So for part three, we are going to look at the difference between the adiabatic saturation temperature equations that we need to derive and the wet bulb temperature. And so in this example, we're going to have some infinitely long tube with some mass flow rate of air going in, starting at temperature and pressure, becoming fully saturated in the end. So here it's going to be fully saturated. And this is adiabatic. It's going to be steady state, so the enthalpy in is going to be equal to the enthalpy out. So we're going to use this equation here to get our equation for the adiabatic saturation temperature. Then we're going to compare that to the wet bulb temperature. Okay, so first we need to start with the enthalpy that's entering the system. It's obviously going to be some quantity times the mass flow rate of air. So we'll just start with the mass flow rate of air. And then we're going to want to multiply that by the heat capacity of the air, and find the temperature difference between the initial temperature and our reference temperature. But in this case, since it's a infinitely long tube, fully adiabatic process, our reference temperature is going to be 0. So we're just going to multiply that by the temperature in. And then we're going to have to add the heat of vaporization. We need to make a note here that this heat of vaporization is in joules per kilogram. In the previous example, our heat of vaporization was in joules per mole. And so then we're going to multiply it by the pressure and the molecular weight of the water. And since our heat of vaporization here is in joules per kilogram, we're going to have to divide by the ideal gas constant times the temperature. That way we have our units fixed. That's pressure of the water times the molecular weight of the water divided by ideal gas constant and the temperature. But we have our mass flow rate here, which is in some kilograms per second. That's what we'll say, and that's kilograms of the air, obviously. And so we'll need to get the units right between these two sides. So we're gonna have to pretty much multiply by the reciprocal of this, except it's going to be total pressure and the average molecular weight that we're have in the numerator. Oh, in the denominator, sorry. I have to multiply by the reciprocal. All right, and then from this, you'll see that the ideal gas constant and temperature cancels out. So we can just reduce this down to one equation like this. So we'll have the enthalpy in is equal to the mass flow rate of the air times, I guess I don't need that parentheses here, times the heat capacity times the temperature in. And we're going to add the heat of vaporization and multiply that by the pressure of the water times the molecular weight of the water divided by the total pressure and the average molecular weight. Okay, so this is our equation for the enthalpy entering the system, and now we need to find enthalpy leaving the system. So we're going to make a very similar equation. So we're going to have our mass flow rate of air, that doesn't change. And we're going to multiply it again by the heat capacity times the temperature leaving the system. So it'd be, because we want the enthalpy out, so temperature out. And then again, we would subtract some reference temperature, but like I said before, we don't need the reference temperature because it's a adiabatic process. So then we're going to add the heat of vaporization like we did before, but at this point it would be completely saturated, so we will need the saturation pressure times the molecular weight, and then we would also, it'd be a similar to the enthalpy in. We're just going to divide by the total pressure and average molecular weight. Alright, and so we know that the enthalpy going out is equal to the enthalpy going in, like I said up here, so we are going to set the equations equal to each other. So here's the equation for the enthalpy in: mass flow rate of air times the heat capacity times the temperature in plus the heat of vaporization times the pressure of the water times the molecular weight of the water divided by total pressure and average molecular weight. And we'll set that equal to the mass flow rate of air out times the heat capacity times the temperature out plus the heat of vaporization times the saturation pressure times molecular weight divided by the total pressure times the average molecular weight. Okay, and so you probably notice now that we have our mass flow rate on both sides, and we also have our heat capacity and our heat of vaporization, and this group here, the molecular weight divided by total pressure times the average molecular weight. We have that on both sides. So we can condense this down a little bit. Let's scroll down just a little bit. We can factor all of these out. So then we get our heat of vaporization times our molecular weight times the difference between the saturation pressure. Keep using the same notation. The saturation pressure minus the pressure. No, I have that backwards. It'd be the pressure minus the saturation pressure is equal to the average molecular weight times the heat capacity times the total pressure times the difference between the temperature out and the temperature in. And so now we are going to take our equation that we found up here for the wet bulb temperature. We're going to compare the two, so I'll just rewrite it down here. So this will be the heat of vaporization times the pressure of water at the surface minus the pressure of water in the environment is equal to the total pressure times the heat capacity times the difference between the environment, times the difference between the temperature of the environment minus the temperature at the surface. Okay, so now we're going to want to compare these. So here we have the quantity of, we have the heat of vaporization times some difference in pressure. So yeah, so for things that are similar, we have some heat capacity, or the heat of vaporization times some difference in pressure. And we also have, I'll mark this, and we also have the heat capacity times total pressure times a difference in temperature. So that's also the same. Some differences that we have. We are multiplying by the molecular weights. So the molecular weight of, on the left side of the equation would just be molecular weight, and then we are multiplying the average molecular weight on the right. And the heat of vaporization for wet bulb is in joules per mole, while the heat of vaporization for the adiabatic saturated temperature is in joules per kilogram.